Yeah, that's fine. We're running the world. Yeah, that's the general rule. People shouldn't care about these presentations. I mean, you can like go up and down and so on, but their presentations will be ready when they come on stage.
Okay.
And here they have also a clicker that is on. It's also with a
Yeah.
pointer.
Okay.
So yeah.
Okay. Yep. Good. 2 minutes. I think I say punctual here. The bell does it.
Yeah, the bell is, it's amazing.
Yes, I put it there. Sorry. Hold on. Just found one.
That's recording.
It's already recording.
Yeah. There's a pointer, and is it working?
Yeah.
Yeah, it's working. All right. All right. Thank you, everybody. Thanks for coming back on time. That gives us more time to drink, as I mentioned earlier this evening. So we'll start now with the sessions. And the first session is skills assessment, calibration, validation, and uncertainty. And Gideon is going to be in charge of this. And there is a pointer for those of you who don't know. We didn't mention it earlier, but there is a pointer. So for those of you speaking, the pointer is here. So I'll leave it to Gideon.
Thank you, Gina. Okay, hi everybody. My name is Gideon Gale, and along with Jeroen, Simeone, and Ekin, we'll be chairing the very first session of this conference. The session deals with skill assessment, calibration, validation, uncertainty, and as all modelers know, these are the key steps in establishing a model that we can rely on to use and apply to the various ecosystems. There's a great list of talks. There are 6 talks in this session, and all of them will be really interesting talks. Our first speaker will be Jacob Bentley, talking about calibrating ecosystem models to support ecosystem-based management of marine systems. Pointer there.
Hi again, everyone. So I'm Jacob Bentley. I'm Principal Specialist Marine Ecosystem Modelling at Natural England, which is a government advisor for the UK. And they did not give me a jacket, so I can't represent them at the moment. But I'm going to be talking about some work that it happened over a few years. It was kind of a bit of a passion project. Started way back from, I presented the model 5 years ago at the conference on the Irish Sea. And we used a calibration approach for that model, which was relatively new. And we wanted to publish a paper about it because people started to use it. But when we started diving into calibration approaches for Ecopath with Ecosim, we found that there were other approaches which we knew that people were starting to share. And then there are a whole load of different approaches for calibrating models that people were using. And there was almost kind of no systematic way to assess which calibration approach was the best. Or oh, louder. Yeah. So there was no real systematic way to assess which calibration approach is best or how different calibration approaches impact the outputs of your model. So we worked on this paper together, and a lot of the co-authors are in the room, and they've volunteered to answer all the questions afterwards. So the basis of the paper and the work that we did, it was around the fact that these models are being picked up more and more now for use in operational context, like Howard said, to be used for ecosystem-based management. And a large part of that is using these models to assess uncertainty, look at trade-offs, and look at risk. And as a community, we've got quite good at handling these things. When I went to my first ecosystem modeling conference, which was about 10 years ago now, it was all about uncertainty and the fact we're not doing anything to look at uncertainty. And when you look how far we've come in those 10 years, we're now using lots of approaches to look at structural uncertainty, climate uncertainty, parameter uncertainty, and we're getting quite good at it. And we're learning that our models are relatively good in the realm of strategic advice. But what we don't really do when we're building these models, or some may not, it's kind of not really out, and it hasn't been out in the open domain, is we don't look at the uncertainty around the calibration approaches we use. And those of us that have used Ecosim and have calibrated our models to time series to make sure our observations can replicate, our simulations can replicate observations, know that this step can be quite a large source of uncertainty and bias. So we need to get a better handle on it. So this is vulnerability multipliers. So one of the best things about Ecosim, and the thing that makes Ecosim is that it's based on a foraging arena approach, or it has a concept within it that acknowledges that prey aren't consistently available for predation by their predators. There's going to be a proportion of the population that's available or vulnerable or vulnerable to predation, and a portion of the population that's not vulnerable to predation. And there's a rate of exchange between these two pools. And this is accounted for in the equation in Ecosim for consumption, so how much a predator is eating a prey at any point in the time step. And there are these terms in here. So you have the VIJ here, which is the vulnerability. And that's the vulnerability of prey to predation at any point in the model. And that's calculated based on the natural mortality or in Ecopath, so the base predation rate, and this vulnerability multiplier, which we use to kind of add an upper limit to how much predators can consume if their population was to increase. So if you were to stop fishing a predator and its biomass would increase, what's the upper limit to the consumption or the predation pressure that predator can put onto its prey? So when we're playing with Ecosim, we don't actually touch vulnerabilities in these equations. So what we play with is these vulnerability multipliers. And for those of you that have worked with it, these span from, well, the default value in Ecosim is 2. It can range from anywhere between 1 to infinity. So a value of 2 here would suggest that the population's able to double its predation rate based on what it was in Ecopath originally. And these vulnerability multipliers have a huge impact on the carrying capacity of the species in your model. So you look at this figure over here on the right. So these vulnerability multipliers, they'll determine the predator carrying capacity. So you can see down here, this is these lines represent different vulnerability multipliers. On the x-axis, you have the unfished biomass over the Ecopath biomass. So it's essentially what the carrying capacity can reach and how that predation pressure is then passed on to the prey. So with the higher vulnerability multipliers, you can see your stock can reach increased levels in the model and exert greater predation mortality onto the prey. Ecologically, we've linked this. I mean, people link it in lots of different ways. If you go to different courses that teach EWE, people will link it to vulnerability multipliers to top-down and bottom-up effects, where a vulnerability multiplier of 1 means that the prey is largely driving any increase in predation mortality, whereas a high vulnerability multiplier will suggest that an increase in that predator's biomass will highly impact the prey. But the way that I like to think of it is in terms of this carrying capacity and the fact that if you release a stock from fishing mortality, what carrying capacity could it reach? And these vulnerability multipliers are a way to lead to that. So it's relatively accepted that this is needed in these multi-species models. We need to acknowledge the foraging arena and that prey aren't always available to predation. But how we do it is up for debate. There are lots of different ways to do it. So one of the first steps you could do is use a prior information. So knowledge of the ecology of the species. At what level has it been depleted to? What are the different life traits it might have? Does it hide? Does it show? And how might this impact how much is vulnerable to predation? So you can alter these vulnerability multipliers in the model just based on this information. But more and more, we're starting to move to more statistical ways to estimate vulnerability multipliers. So we're using routines that are manual. So there's a manual fitting approach in Ecopath of Ecosim, and there's an automated fitting approach in Ecopath of Ecosim, where you can estimate the vulnerability multipliers so that you change the predation mortalities of the prey, and you can change how productive predators are, so that your simulations will fit observations. So these statistical routes are being used more and more, but what we don't really know is how sensitive models are to these statistical pathways and the ones that we choose. So for this paper, we carried out a couple of case studies to try and investigate, okay, how do these different vulnerability multipliers impact the way the model works, looking beyond the way that we normally do it. So for those of us that have fitted Ecosim models before, the thing we're often most interested in when we estimate vulnerability multipliers is making sure that our models can replicate observations. And we often stop there. So the set of vulnerability multipliers that are best able to replicate observations are the best vulnerability multipliers. They lower the sum of squares and they give us the best statistical inference and best fit model. But it goes beyond that, because when you think back to how these multipliers work, we know that they impact carrying capacities, they impact how species interact in the model and how vulnerable things are to predation. So while they'll improve your fit, all these different approaches might lead to good fits in your model, but they might lead to wildly different estimates of environmental indicators or estimates of fishing MSY, so maximum sustainable yield. So we developed two case studies. The first one, we went back to school and used the anchovy bay model, which is often used in a lot of lectures and teaching when we do EWE. And here we wanted to see, is it possible for vulnerability multipliers to re-emerge? Can the model accurately guess or estimate what the right vulnerability multipliers are for the system? So to do this, we made a fake hypothetical model. We entered what the vulnerability multipliers are for the system, and this is based on our ecological understanding of certain things. So we said cod is relatively overexploited in the system, so we give it a vulnerability multiplier that's quite high, so it's something like 10. So that means when you reduce fishing mortality, it can go to a higher carrying capacity. So we made a fictitious model with fictitious vulnerability multipliers, and from that, we were able to extract biomass and catch time series. We then took those biomass and catch time series and used them as calibration data to see if, when we refit the model using this calibration data, will those vulnerability multipliers that we put in originally re-emerge? And we looked at whether, if you add noise to the data that's coming out, is noisy data, does it lead to the same vulnerability multipliers? So you can see on this plot here, we did this so in Ecosim, you can estimate vulnerability multipliers by predator or by predator-prey interactions. So you can suggest that the relationship between prey and predator in terms of vulnerability multipliers is consistent for a predator's entire prey portfolio, or it's different for predator-prey interactions. So for some species, you can see when we put the calibration data back in and wanted the model to replicate or estimate new vulnerability multipliers, they're relatively consistent with what the vulnerability multipliers were originally, and these emerged quite well. When you started to add noise to the data, the vulnerability multipliers changed slightly and they weren't as accurate. And this had impacts on the relative biomass and carrying capacity of the stock. So you can see different vulnerability multipliers, even though the fits might have still been quite good, led to different carrying capacities if you were to release the model into the future, and also different estimates of FMSY. When you then go on to do this for predator-prey vulnerability multipliers, so that was predator, it gets a lot less consistent. We see that there's large differences in the vulnerability multipliers that emerge across all of the different types of data uncertainty. Where we had noise, it didn't really matter with or without noisy data. I mean, it got a little bit worse with noisy data, but without noisy data, we were still finding vulnerability multipliers were very different to those ones we initially estimated. And again, that had a knock-on effect on the carrying capacities, but also FMSY estimates. So there's a lot more going on here. I mean, the parameter space that you've got here to estimate predator-prey vulnerabilities is a lot larger than the parameter space you've got to estimate predator vulnerabilities. So you're more likely to find different combinations of vulnerability multiplier estimates that lead to good fits. So you see this larger disparity between the two. For our second case study, we took two models that are existing and actually used in advice. So the first is the Northwest Atlantic Continental Shelf model, which Howard shared earlier. So this is a model developed by Dave, which is used to develop ecological reference points for menhaden and striped bass, and the Irish Sea model, which is used to develop fishing reference points for the Irish Sea. So these are both used in advice, and we were curious about how different fitting approaches would impact these models that we're already using, how it would impact the different data that comes out of them, not just the fit. So we looked across multiple different ways of fitting the model. So there are different schools of thinking. So one of the ways you could fit the model is to estimate vulnerability multipliers limited at n-1, so one less vulnerability multiplier than the number of calibration time series you have. That's kind of in agreement with the degrees of freedom you should have. That's in Shealer's best practice paper, for example. The other is to estimate predator vulnerabilities for groups that have time series only. So when you have a time series, it's much easier to constrain what these vulnerability multipliers might be, because if you don't have a time series and you estimate vulnerability multipliers for a group, it's more likely to generate a trend that it might do well for that group, but it's what it's trying to do there is optimize the fit of other groups. It doesn't have anything to constrain itself. So it can be quite wildly different, but it might improve the fit for other groups. So that's something to be aware of. We also use the automated stepwise approach, and then a repeated approach that Dave's developed. And there's the approach which we use for the Irish Sea, where we have predator vulnerability multipliers and predator prey vulnerability multipliers combined. And we found that when you use these different approaches, you do get different outputs, even in these models that have been quite rigorously reviewed. So it is important. It's something that we do have to consider when we're working with Ecosim. We should explore these different routes just as a term of sensitivity analysis of our parameters. But for some instances, you see some consistency. You see some broad differences between different fitting approaches. So the solid dots are using predator vulnerability multipliers, whereas the hollow dots are using predator prey vulnerability multipliers. So you see some differences between approaches that start to emerge as well. And we found that some of the indicators were relatively consistent. So things like trophic level of a community didn't really matter what the fitting approach you used was, because even though the community had rearranged slightly, those indicators had kind of been balanced out by increases in comparable trophic levels in the system. When you increase the complexity of the model, so this one here is for Dave's model, which is a model of intermediate complexity. When you go to the Irish Sea model, it gets a bit more different. You see a little bit more divergence in the outputs, in the indicators. And this is because there's a lot, the parameter space to estimate these vulnerability multipliers is a lot larger. So it's something we need to recognize as well in the size of our models. So final slide. So we have some summaries and recommendations, which you can take and leave. I mean, they're really good summaries and recommendations, but this is, it's kind of a, I think vulnerabilities and the way we estimate them isn't set in stone, and there is a lot of room to do what you need to do, but it has to be justifiable. And I think this can guide that approach. So the first recommendation is to limit the parameters from this work. So you have to estimate, or you should potentially estimate by predator. We know there's a lot more uncertainty if you go into predator prey, but if you can justify it, then that's the important thing. And avoid statistical estimation for groups without time series. So ideally, I think the way that I'm moving forward from doing this work is when I estimate vulnerability multipliers for my models, I'm going to be looking mainly at using predator for groups that we have time series for. So going beyond just looking at fit, checking carrying capacities and evaluating whether they're plausible into the future, conducting sensitivity analysis. So this is what I said about running your models under different calibration approaches and seeing if you get the same outputs. Identify performance metrics, so looking beyond the goodness of fit to see if you can validate your model against other parameters. And we did this for the Irish Sea model and the North Sea model when we got ICES key runs. We used FMSY as a proxy to evaluate the suitability of vulnerability multipliers, and then provide justification. So we know that these are supposed to be tied to ecology. Can you explain how what your model is potentially estimated or what you've entered manually is linked to ecology? I think that's it. Thank you very much.
Thank you. Unfortunately, we are out of time. Okay, that was really interesting talk. And so catch in at the break. I'm sure people have lots of questions for you, Jacob. So our next speaker will be David, calibrating ecospace models with the WE console application and script-based parallel processing. Please.
All right, good morning, everybody. So today I'm not going to talk about a specific model that I'm working on. Instead, I'm going to talk about some work that's really been going on like behind the scenes of all the models that I'm currently building. And this is something that is actually started with a former PhD student of mine, Daniel Velas. Holden Harris, who is here, was a postdoc. He picked it up from there. And we're still trying to improve this process. This is a work in process. And I'm really interested. I know I'm not the only one thinking about this, so I'm interested to get feedback from those of y'all who are trying the same things. So first of all, you know, many challenges that face fisheries managers are implicitly spatial, and so they require spatial modeling approaches. And so, for example, in some of the work I've been involved in, you know, accounting for predator-prey seasonal overlap in Atlantic menhaden and striped bass is really important. Also localized depletion of forage fish and the potential ecological impacts of that. Quantifying spatially restricted the impacts of spatially restricted stressors. It's a lot of S's. For example, with the Florida red tide, looking for explanations for potential environmental regime shifts, which is something we're faced with in the U.S. South Atlantic region. And then also as stocks are redistributing across management jurisdictions, which is pretty much happening everywhere, how does that affect allocation and management advice? So I work a lot at the intersection of stock assessment and ecosystem models. And so in fisheries with stock assessment, you know, models must demonstrate that they can produce reasonable fits to data before they can be deemed reliable enough for management. And so there's a lot of money that's invested into these data collection programs that feed into the stock assessment process. And all the stock assessment models are required to kind of show how well they fit the data, whether it's time series or age or size composition data. However, when we go to ecosystem models, we don't usually confront the models with the data with the same amount of rigor that we do with single species models. And as Jacob just showed, you know, we've made a lot of progress with EcoSim, and we've had the ability to fit EcoSim models for 20 or 25 years now, but we don't really have the same approach for EcoSpace. And there's several reasons for this. One is it takes a long time to run an EcoSpace model, especially if you have a fine grid cell and a lot of species in your model, and you have a larger parameter space than you would an EcoSim. Also, EcoSpace was designed for simulation. It wasn't really designed for estimation. So we have to come up with some type of procedure to really confront our EcoSpace models with data. So this is a work in progress. Put on your helmet, something bad might happen. But our goal is to develop this procedure for calibrating EcoSpace models and bringing the data to the models in a little bit more rigorous format. And so the objectives of doing this are, there's several objectives. One is to statistically compare EcoSpace models with observed data and accounting for the uncertainty within those observed data. Compute this overall cost function for minimization. So in EcoSim, we have the sum of squares measure that pops up on the screen and you know how well you've done. We don't have that for EcoSpace. Another thing we can identify with this procedure is we can reveal what are the most sensitive parameters in an EcoSpace model. We can identify, ultimately we want to identify sort of a confidence set of model configurations, similar to what they do with oceanographic and climate models. You know, what would be our ensemble of confidence models? And maybe eventually land on a best run configuration for EcoSpace. And we need to be able to automate this and have it be computationally efficient. So we do this with this Ecopath console application. I'm not sure how many of you guys are aware of this. Jeroen's teaching a class later this week that I think will introduce it to you. But essentially it's a script-based way to run EcoSpace or EcoSim. And you can load this command file that has these parameter taglines, and you can manipulate the different parameter values and run EcoSpace. So you can use R or Python to write out a whole bunch of these files and then call EcoSpace using R or Python. And this can all be parallel processed. If you have a multi-core workstation, I have a big computer in my lab, so I can do, you know, 100 EcoSim runs in 10 minutes versus one run in 4 minutes. So it really changes the game for how we can run EcoSpace. So thinking about the different types of data that we can bring into EcoSpace, we basically have our biomass and catch time series. You can bring that straight from your EcoSim time series file. But EcoSpace also produces these biomass distribution maps, and we need to figure out a way to statistically compare our observed data, spatial data with observed maps. And these could be mean catch rates by grid cell or species distribution model outputs that we can confront EcoSpace with there. We also have effort distribution maps. Haven't really gotten into that yet, but if you have data on spatial fishing effort from vessel monitoring systems or fisher logbook data, then you could also make that comparison. We also have the ability to extract the age composition data from the individual based model. I think me and my former student Daniel are the only ones to actually ever look at that, but it does exist. So stock assessments rely a lot on age composition data, and the ecosystem models can produce similar types of predictions. And also haven't quite gotten to this point yet, but like relative effects. So if we had a study that said like before and after a red tide, what was the change in biomass? Ecospace also predicts a same type of experiment that we could then compare with those results. So you have to what we're trying to do here is boil all this down to one number that we can minimize in ecospace. All right, so this is our objective function or cost function. So the calibration procedure, this is something that we've kind of cooked up in our lab over the last few years. First place I'm presenting it, probably the only place where I could present something like this. But essentially we start with a sensitivity search. So we write out a bunch of command files that change each parameter value just a little bit, and we keep track of that likelihood of the objective function. We can then say, okay, let's take our most sensitive parameters, and then we're going to iterate over a series of test values for each of those parameters. And if there's no improvement in the likelihood function, then there's no change to the parameter values. If there is an improvement, then we will retain that parameter value and continue the calibration procedure. And we can continue that until, for a number of parameters and sequentially calibrate one parameter at a time. That's where we're at with it right now. We want to move beyond that sequential stepwise process, but we can step through each parameter, and then you can repeat this whole analysis as many times as you want to repeat the sensitivity search and see if more sensitive parameters emerge. You can also think about doing this in phases. And so this is one of the approaches I've taken recently, where, for example, with the red tide application, we want to make sure that we get our species in the right place so that the red tides are impacting them at the right place and time. And so in the first phase, we try to focus on getting the spatial distributions right. And in the second phase, we focus on fitting those temporal distributions. And so fitting the spatial patterns, we tend to focus more on the environmental response curves, whereas fitting the temporal patterns, the vulnerability parameters become more important. Of course, they're correlated and they're all, sort of interacting with one another. So again, that's a big parameter space to explore. As we get to sort of phase 3, we might add more detail as far as the other mortality forcing. And so you can think about running these iterations in different phases and turning on different parameters. This is not entirely unlike what we do with big complex stock assessment models, where we'll estimate parameters in certain phases. And so a lot of these ideas were sort of taken from how we do single species assessments. So now I'm going to talk about some applications real quick about how we're doing this. This is the West Florida Shelf red tide model. This is actually where this all started. Daniel Vilas, my former student, published this in the paper, and SOAR is the first one to kind of work out this iterative process. And so we actually have funding to continue this model over the next 4 years. So we're going to continue working on this specifically for Florida red tide. The other model where we've applied this recently, I think we've had some pretty good success here. And this was where Holden picked up the calibration routine and attempted to calibrate this model, the Suwannee River estuary here, that was driven by this land use and hydrological model that informed the dynamics in the estuary. And we have long-term monitoring data. These are all the blue sites here are fish collection sites by the Florida Fish and Wildlife Research Institute. And we do the calibration procedure worked actually quite well here in this case. And I think it was because we had a localized system where we knew that all the drivers were pretty much captured within this model. So we had a pretty good success here calibrating the Suwannee River estuary model. Again, everybody's favorite model, the menhaden mice model. We have funding to build a spatial model for our NWAX mice and Atlantic menhaden model. But this is because when we finished our ecological reference points using EcoSim, the first thing the managers asked, well, what happens if, Atlantic herring come back and striped bass are migrating further north? And so the questions immediately became spatial. And so we were able to get some funding to build out the spatial model. And so we're going to attempt to calibrate that. And I think with this mice model, because it has such a fast runtime in ecospace, I think we'll be able to make a lot of progress as far as calibrating ecospace, and maybe even instead of doing that sequential parameter step through, actually get into some more like gradient descent function, so we can actually look at multiple parameters simultaneously. that are the 3 or 4 most sensitive parameters and identify, what would be the best values there. So this is all a work in progress. And then lastly, you'll hear more about this model. Lauren Gentry who's leading this project, is giving a talk later in the week. But this is a case study in the South Atlantic region of the U.S. This is our management region. It's not the Southern Atlantic Ocean, but the Southeast Atlantic coast, where we've actually seen precipitous declines in recruitment and abundance indices across the shelf now for a little over a decade. And so several hypotheses about why this might be happening include recruitment overfishing, oceanographic changes. They've noticed some changes in the Gulf Stream and how that drives primary production especially benthic primary production on the shelf where these species reside, as well as predation from a quickly recovering red snapper stock, as well as invasive lionfish. And so we want to be able to develop this model that's calibrated the data and then be able to do some hypothesis testing to eventually try to determine, what are the most important drivers in this system causing these declines. All right, so that's all I have. I'm hopeful that I can come back in 5 years and say we've got this procedure worked out and we have a button that you can push and we can then help to calibrate our ecospace models better. So hope to have these conversations over the week and see where it goes. Thank you.
Thank you, Dave. We have time for a couple of questions.
Hi, Dave. Thank you for the talk. It was really great. So the spatial comparison, do you have like species distribution maps for all the species in the model, or how do you cope with like those species where you drive them or don't have species distribution models to compare
so like
observation?
in our big models, we don't have data for all the species, but usually the mice models that we're building are built around the species that we have a lot of data for. And so like, for example, the Menhaden model and the South Atlantic model, we have trend data and distribution data for most of the species in that model. And so we'll be able to actually confront the model across all the species included. So I'm scared.
No, Dave, don't. Given that you are in the US and you're using R for repeated runs here, why are you using the big model and not RPart? Are you using RPart?
No.
Why not?
It doesn't do all the things I needed to do. Simple question, simple answer.
Hi, so Dave, what's this? So I have a question here. I think it's a very interesting presentation. Great job. And we always got to pick it up by not your model does not fit well for 1 or 2 time series. I'm wondering, so one thing to talk about that is say, we don't care those species. So one thing to say that is to put a different weight on different time series. I'm wondering your comments on that, and will that make this process more complicated?
It doesn't complicate things at all. In fact, we've already built that into the objective function. So you can weight each component of the objective function or each time series, just like you would an ecosim. So we had that ability. I just didn't go into the detail here, but yes, you can weight your data however you would like to, whether based on the variability or the certainty within those data, or if you just have a priority for certain species over others. So that capability is there.
Thank you.
Great. Thank you, Dave. So our next speaker will be Christy, talking about a new tool for food web model validation, Louisiana case study.
All right, everyone. Oh, God. Just stand over here. Hey, can you hear me in the back? All right. Yeah, so I'm going to talk about a validation, which is something that modelers want to do, but generally because we're using all of our data, we can't do validation very well, or if at all. And it has to do with everything in this session, the high data needs. If we're generally looking at proportions of data that we have to use it all, we can't parse any of it out for the validation. And we're also using, and specifically for diet data, we're generally using outdated sources. Diet data are very expensive to collect. And there's some really great genomic approaches coming along that could help with that. But right now, the data in our particular models that we've been building are not necessarily the most recent. And if you've ever used Fishbase to build diet data, it's probably not from your location of choice. So one way to go about addressing this issue is to think about, can we get this information in a timely manner from in situ data, right? So stable isotope analysis is one way to do this. And this is something that I think Kim de Mutsert has been thinking about for a long time, and kind of where this idea came from. We can evaluate the use of these stable isotope signatures to evaluate not only the basal M members or the productivity in the system from phytoplankton to seagrass to marsh grass, but we can also understand the precise location, the precise time period, and then calculate the trophic levels using the stable isotope analysis. Now, this has already been done. If you've read any papers out there, you stable isotope people, you've seen that they're doing it, right? So they're taking the food web derived trophic levels and they're comparing it to the stable isotope derived trophic levels. But one of the problems is that there is just not a lot of thoughtfulness about what you do after you get that answer. So what we're finding is that most of the previous studies that have looked at this are the food web models underestimate the trophic levels when you compare it with the food web model underestimates compared to the stable isotope. One overestimates, and then a few of these studies kind of do a little bit of both. But like I said, but why? Why is this happening? Why is there discrepancies between the food web model and the stable isotope data? And then once you do find a difference, what should you do with these findings? So our approach in this study was to use Bayesian statistical models to derive the stable isotope, which if you're stable isotope people, this is the way we're doing it now. And then also develop a visualization tool, because this kind of depiction of trophic levels from Ecopath being on the x-axis and the trophic levels from stable isotopes being on the y, you see overestimation, underestimation. So this visualization is okay for those of us who are used to it, but if we're really trying to use this for resource management, it's not a very, exciting or approachable way to show trophic level analysis. So we wanted to develop a visualization tool to get at this. Don't know what happened with the format here, but that's all right. So we also want to provide suggestions to mitigate the inconsistencies that we potentially could be finding between the food web model. And then ultimately, this is a data transparency thing. So if we're really going to unpackage these things and want resource managers to use it, we need to be transparent with how we're doing it, and so that they know this is a robust tool to make their management decisions. And so in this study, we wanted to build it. We had to have a comprehensive database for the food web model trophic levels, and then the ones derived from the stable isotope data. And so these stable isotope data were already existing in the system. So if you know there are stable isotopes in your systems right now, you can do this. And then we would take that database, run it through the code, and build a validation visualization tool. So it's just a visualization tool. It's not doing the validation, to be clear. Then we run the case study, and then we wanted to kind of revisit. This is kind of one of those things like, yeah, we probably need to see what the previous studies did. So we just ran a couple of correlation analyses as well to see how our analysis kind of stacked up to the previous ones. So the case study we're using is work that Kim and I have been, working almost 10 years now, I think. So lots of papers have come from it. And so this is an actual model that's been used for environmental decision-making multiple times now. And so this is a pretty well-accepted model within the system. And so now we're kind of doing something similar that Jake did, like going back and looking at a model and see how it evaluates in this way. So can't go into any of the methods really, but we took the trophic position package in R, which is what we use to process the stable isotope trophic levels, took the trophic levels from Ecopath, and then we created a new database. That's the fast version. All right, so you have your stable isotope data, and you run it through the Bayesian model. You get your trophic levels, you get your Ecopath trophic levels, gets in the database, we get all the functional groups, get them in one place, run it through the Shiny app, and then hopefully out pops all of these great understanding validation plots, provide some summaries and things like that. And what Jeroen doesn't know is that I really want to build this into a package and plugin for everyone to use. And so this is really just the first iteration of that. And we have funding to do it, so we can do it. All right, so, and then again, we wanted to do a comparability study with this Spearman rank correlation, which is what all the previous studies have worked on. And hindsight being 2020, which is how we do a lot of the science as ecosystem modelers, we found when we went through this process, we're like, why do we have a less correlated data and compared to previous studies? Well, spoiler alert, is because of the aggregation of the data and the number of functional groups we had in our model comparatively. So we did a little switcheroo here. So we had lots of non-aggregated data. So I think 47 functional groups, and then we aggregated those down into a smaller number to then do a comparison. And you'll see what I mean in a minute. So non-aggregated data. So we took all of these multi-stanza data and put them into what the other previous studies had done. So you can see that already there's probably going to be some differences between the analysis just because of the detail of the data that we were using. So quick results, high level. This is Ecopath on the left, stable isotope trophic levels on the right. And so there's some agreement, there's some differences. This is probably how your data should look. Some of them are better than others. And so we can't go into all of the details on why everything was different. So that's for another conversation over beers later. But we can kind of just take this information, we'll show you how we visualize it, and then we can talk each individual system that you're looking at on how you might need to consider why you see these differences or similarities. So when you open the visualization tool, you'll see something like this, which we think is a little bit better for managers to swallow. So if you just take a largemouth bass, so here's our probability distribution from the stable isotope data. We've got 95% confidence intervals on either side. The white dashed line is the mode trophic level calculated by the Bayesian model. And then our red line is Ecopath trophic level. So in this situation, we would say that these 4 species that we're depicting here are falling, there's agreement between the stable isotope data and the trophic and the EWE model. And so we would say that in this particular case study, 22 of the 47 functional groups fell within the Bayesian derived probabilities. So that means that 25 of the 47 did not fall within the Bayesian derived probabilities. And so this is where the eco-tuner part comes into play. So now you have these 25 groups, and that should make you take a pause and think about, and then go interrogate your data in a way that you wouldn't have been able to interrogate the data before because you didn't have this information, right? And so quickly, we then recreated the non-aggregated. So, right, this is the first thing we did. And we're like, wow, that looks really rough. We're really not doing a good job here. And I think Kim or one of us, we decided, maybe like looked at it and like, why does this look so shitty? And so we were like, oh, they didn't have as many functional groups as us. They didn't have multi-stanzas. And so when we recreated what they did, we kind of made it look a little bit more like what they were calculating with their correlation analyses. So these are just some of the previous studies. And so we felt pretty good about that. I mean, just 47 functional groups compared to much lower ones, that's going to probably provide that output. So the summary of outcomes, we had 4 different goals to kind of look at in the study. We had 22 groups that fell within, 25 groups that fell without the bounds. And then we found that our aggregated data aligned more with previous studies for the correlation analysis. So we cannot get into all the potential explanations of why the trophic levels differ, and you're going to have a million ideas yourself. But in general, here are a couple of the things that we considered when we saw the differences in the model. So we had 31 different data sources for this. So I built this model during my postdoc with Kim. So 31 different data sources for the model. 20 of those sources were from pre-2000, and we parameterized this model for the year 2000. So that's already one issue. But then we looked at all the SIA data that we used that went into this analysis, and all of those dates for those samples were collected after 2001. And so already you're getting this misalignment if you're thinking about changes in geographic distribution and changes in all of the things that are going on considering global change. And this is a problem that all models, quote unquote, are going to deal with as a food web modeler. So you should think about this, is that detritus is automatically one in our food web models, right? And so, but we know that detritus is dead and decaying plant and organic models. So it's inherently, all models are going to have a lower trophic level, especially if it's really derived from a system like an estuary or something like that. So it's not necessarily a problem or something that we need to address, but it's something that we can consider, and likely the reason that many of the models underestimate trophic levels when compared with in situ data. And so the correlation analysis, again, many of the previous studies lacked multi-stanzas, that we had more functional groups. And then we contend that the lower correlation value, even with the 47 functional groups, still captures a lot of the natural variability within the system, right? We're trying to recreate a natural system that's super dynamic. So even though the correlation was 0.56, we still feel that that's pretty darn good in that case. I think that was my last slide. So if you want to check out EcoTuner, you can just have a look on your phone. Now that's going to be specific to our case studies. So the goal in the future is to, he doesn't know this until now, I want to work with Jeroen to build this in as a plugin, or just maybe something separate that everybody can get at. So if you have ideas on how to make this even better or stronger, please come and chat with me about it. But thank you.
Time for a couple of questions.
This thing on.
Okay, brilliant. Thank you. That was an awesome talk. It was really interesting talking about the misalignment in the time of the data. I was wondering if you thought about, or if you had a look at the change in the trophic level over time in Ecosim, and whether you could look at like a distribution in Ecopath trophic level as well.
I haven't looked at that, but that's a great idea.
All right, cool. Cheers.
Thank you. I was really happy to see that you had the diet composition as the background in one of your slides, but you didn't talk much about diet composition. Have you considered tuning the diet composition as the way of making it match?
That's one of the suggestions, right? So if you, that would be like one of the suggestions that pops out. So if you went back, if you found that largemouth bass wasn't fitting well, then you would go back to the diet and interrogate the diet. So I didn't have much time to go into that, but that is exactly one of the suggestions that comes out from this. I mean, we do that anyway, but we don't generally do it as informed as this. Does that make sense, right?
Hi, Christy. Most of the figures that you showed had the Ecopath estimated trophic level lower than the stable isotopes. Is that like a consistent bias, or?
Yeah, we think it's the detritus issue as part of it, just because this is an estuary and it's huge. The detrital pool is huge compared to the other basal M members. So we suspect that's one, but if you have ideas on why that's the case, but it's across, as you saw in that Venn diagram, it's across most of these analyses that folks have done.
Sorry, just really quick follow-up on that, because I thought that detrital issue was super interesting. And I was wondering if you have a way of correcting.
Kim, you want to talk about it? We've talked about this a ton, and we don't necessarily think that it's a correction that we need to make, is kind of where I feel like we've landed.
Yeah, I was, yeah, we became hesitant about doing that, because if a detritivore eats a decaying shark, you're now giving it a trophic level of 4, and it just didn't seem ecologically sound to do that. So I didn't want to.
I'm thinking back at how we programmed the trophic levels for detritus, and that's thinking back 30 years. I don't think there's any problem in changing that to what trophic level. Do you actually measure what the trophic level should be?
That's the thing,
Can
is
you
I was
give us
like,
some
where do you get your
guidance on
detrital
this? Where will
numbers?
you get it from?
Yeah, we just make that up. You know. I have to go. I don't
Yeah.
want to take
We
someone.
need to move on. Thanks, Christy. Okay. Whoops. So we can move on to our next speaker. You have it? Oh, I have it here. Okay, so Sarah is going to be our next speaker, talking about uncertainty-based approach to analyzing network attributes of food webs in Northeast. Oh, okay. So yeah, talk about uncertainty-based approach to analyzing network attributes, food webs of Northeast U.S. continental shelf.
And you see that there's little symbol because they're students, so you can vote for the student presentation. Sorry for interrupting.
Okay.
Cool. All righty. Hi. Oh, yeah. Okay. Okay. Hello, my name is Sarah Weisberg, and I am nearing the end of my PhD at Stony Brook University in New York. This work has been done over many years with collaboration, largely with some wonderful folks at the Northeast Fisheries Science Center. And you can see their names there. So we are using Ecopath, and we set out to build, to model the area relevant to the Northeast Fisheries Science Center, which spans from Cape Hatteras to the Gulf of Maine. And I really liked what you were saying earlier about trying to right size the model. So, do you model the whole shelf, as of course has been done? Do you model it in smaller chunks, which has also been done? And we decided to use the ecological production units that are currently used in management contexts, because that was sort of our thoughts around what spatial scale was the most relevant. So these are the Gulf of Maine, Georges Bank, and the Mid-Atlantic Bight. And these three Ecopath models are parameterized for the early 1980s. They're developed with the same data sources because we wanted to compare between adjacent regions. And what are we comparing? I'm most interested in some of the network analysis metrics. So looking at the whole food web, what can we learn about the food web? And really, are these systems, we're managing them as if they're different production units, are they fundamentally different at that zoomed out scale? And in particular, I'm interested in this metric of ascendancy, which maybe I should ask for a show of hands. Show of hands, is that word familiar? Ascendancy. Okay, good. I'll take a minute to explain what I mean. So basically the idea here is that you want to quantify the structure of trophic flow in a food web. And I like this figure because you can see that the food webs have the same components and the same connections, but on the left-hand side, you have more weighting of flow through certain pathways. On the other side, on the right, they're more equally distributed, which therefore means that this system is more efficient, but it is also considered to be less resilient, because if you perturb some of these connections, you're more likely to have ripple effects throughout the system. And empirically, it's been posited that there is an optimal value for ascendancy when you scale it to the size of the model. So if you scale it between 0 and 1, the optimum, the goal, or sort of is 0.4 with a range observed in real life ecosystems. Okay, so then built a model. This is not pleasant. I mean, it's pleasant for me to look at, but I don't expect it to be pleasant for you to look at. This represents many years of my life, which actually maybe is unpleasant to think about it. What'd you say? Yeah, it's hard to see this as many years of my life in one slide, but the way that I made these, the colors represent trophic levels, and the boxes are scaled to the biomass in each unit, and the arrows are scaled to the flow magnitudes. So I want to zoom us in on the lower part of the trophic level, the lower part of the food web just a bit, to compare between those models, because it would be ugly to look at all three side by side. You can't really fit them on a slide. No, because it's important to what I'm about to say. So the Gulf of Maine is a deeper basin amongst those three units. And I want you to notice that there's more trophic flow flowing to these two copepod groups over here, and that they're relatively large biomass units compared to some of the other groups in this portion. Compared to the most southerly component, the Mid-Atlantic Bight, wherein we have a rather large macrobenthos group and relatively smaller copepod nodes, as well as flow magnitudes. And Georges Bank is sort of in between. So we have it's basically between. You get it. All right. And so then I can calculate this ascendancy again on a scale of 0 to 1 for each model. And what popped out was that Georges Bank was lower, so less efficient, more resilient than the other two. And I could stop there, but then I would not be in a session about uncertainty. I just gave you one single estimate. Instead, I wanted to incorporate, in this case, parameter uncertainty using a routine developed in RPath by Karim Aiden. And what you do essentially is you say, okay, I can set a score for how confident I am in each and every parameter value in that initial model. With lower numbers being I'm more confident. We have a survey that I use to generate this biomass estimate for haddock. And so I feel like, okay, it's decent. Whereas some other groups, like detritus, as was mentioned, I don't know. So use that score to set a distribution for each and every parameter, sample from those distributions, and generate a new parameter set. And you do that again and again and again. I usually do this 50,000 times. Why not? And sounds nice. I get a suite right now of parameter sets, and then I test each one of those for essentially thermodynamic plausibility, which usually takes the form of if I run this model forward for 50 years, do any of the groups explode in biomass or crash? And that tends to eliminate the vast majority of those sampled sets, but we retain typically 3-ish%, 2 to 3%. So I looked at now the relative ascendancy scores of the ensemble of models that came out of that EcoSense routine. And what I saw surprised me, because 0.33 was my starting value, but the distribution now shifts higher, closer to that literature optimum value. And when I saw this at first, I honestly thought that I did something wrong, which was probably the first thing to think. And then I did it again, and I did it again. I kept getting the same result. And I actually looked, Jacob, at some of your papers, and there were figures that sort of looked like this. So I was like, maybe it's okay. And maybe that's actually telling me something interesting, which is that in the course of this resampling, we're getting perhaps a slightly more, maybe even realistic picture that's closer to that optimal value. And I wanted to know also how much of this shift is due to the elimination of most of the parameter sets. So I compared it. I said, well, what happens if I don't have that restriction? Right? I just resample and retain all of the outputs. And I see two things. One, we still see a shift, but it's not as extreme. So you get a little bit of an extra shift from that thermodynamic bounding. And that was true for the other two regions as well, essentially the same trend. And then comparing the three EPUs, we see two things emerge. One, this unbounded versions are lower in ascendancy compared to the bounded ones. And we start to see a bit more separation between our adjacent regions, with the Mid-Atlantic Bight now looking at as having the highest ascendancy, then Gulf of Maine, then Georgia's Bank. And I wanted to probe what groups might be sort of influencing that shift, particularly the shift from this unbounded to bounded result. And so I looked at the distribution of trophic flow through each groups, comparing that unbounded and unbounded group in each region, and looked at which of those were statistically significant distribution changes. So I'll show you what I mean. Again, here, comparing these thermodynamic bounded and unbounded conditions in each region, looking at which groups pop out. Now, in all cases, you see pretty obviously that this approach, this EcoSense approach, selects for higher primary production, which is intuitive, but also I think important to know when using tools like this to incorporate uncertainty. And we start to see other differences shake out in the lower trophic levels between regions. So sorry. Small copepods, you actually see less trophic flow coming through those groups in this bounded condition. And then when you look at the large copepods, this is our famous Calanus and Marchicus, we see it coming out as important in Georgia's Bank and the Gulf of Maine, but not in the Mid-Atlantic Bight. And when we look at the benthic groups, we start to see that the benthic groups are important in the Mid-Atlantic Bight and Georgia's Bank, but not the Gulf of Maine. So I'll just repeat that because I said a couple of things really fast. Essentially, we are seeing that, or what I think this is saying is that lower ascendancy in Georgia's Bank, this one, is linked to the fact that you can have sort of two major parallel pathways. You can have trophic movement through benthic pathways and through pelagic pathways, giving you that overall redundancy, kind of fundamental redundancy in the system that you do not have in either of the neighboring regions. And to me, that was sort of illuminating as to why we have these distinctions in the first place, and can help bolster thinking about them as fundamentally ecologically different in a way that hopefully can support EBM, ecosystem-based management. Okay, and thank these folks, and most importantly you, for listening to me. Yeah. Yeah. Now let me off easy.
I'll ask one. You don't get off too easy. So when you run your EcoSense routine and you did the 50,000 different configurations, you said that you thinned them out based on whether they crashed or not. Did you also adjust the vulnerability parameters? Like, because they're going to be conditional on whatever your Ecopath settings would be, right? Like,
I did not adjust the vulnerability parameters.
okay.
No.
So I'm wondering if, like, you might still have stable models if you change your predation mortality rates change in Ecopath, and your vulnerabilities might not transfer over as well, causing that instability.
That is a next step that we've been considering. It's like actually sort of taking those EcoSense outputs and trying to tune them, but right now it's just like, is it, we assume that if your basic configuration causes some groups to totally crash out or to totally explode, then that's something like sort of fundamentally unrealistic is happening. And that was building off of the way that this tool has been used in the past by Karim and Andy Whitehouse and some others. So, yeah.
Yes, Sarah, nice talk. Thank you.
Thank you.
What you can also do for weeding out unlikely models is to do, for instance, a pre-bell analysis like Jason Link did. There are several ways to look at, okay, is this, are we numerically in the wrong place here? Good.
Absolutely. That's a good idea.
A quick question for you, Sarah. So talk about the difference in resilience based on those values.
Yeah.
Did you try hitting any of those works with some sort of disturbance that evaluate resilience?
I have not, but that's also sort of on the docket. I mean, part of why we built these for the 80s was to be able to look at changes over time and ask for example, as this region has experienced pretty dramatic warning, have the resilience characteristics shifted? And that's ongoing. But we haven't, I think there's sort of a separate body of literature that says, well, we assume or we posit that this ascendancy metrics are linked to resilience, and how much do we know that, and sort of relying on some of that earlier work. Yeah.
Cool. Thank you very much.
Yeah, my pleasure.
So our next speaker, I think some of you may know Jeroen. Talking about making ecosystem modeling operational, a novel distributed execution framework, the MacGyver pattern.
Yeah, the MacGyver framework.
Jeroen.
Oh, I got the hat. That's kind of nice. Thank you. Nice. So, hi everybody. I'm here to present something I did for my dissertation. I'm taking you to a little bit of another side of the story about uncertainty. Yeah, please go ahead. Next slide. Oh, can I do myself? Yeah. Good. No, there you go. So, okay, for the purpose of my dissertation, I'm talking about spatial temporal models. I call those MEMS, their acronym. And this is basically what been hearing all the time. But there's a persistent shortcoming that these MEMS are not officially calibrated, validated, and assessed for uncertainty, as we've been hearing to. And we wanted to set out in this position paper, the reference is down there below from 2021, why that actually happened to be. So we did a literature review, and that figure over there captures it quite well. You see a red ring there, the technology gap. The story basically comes down on that the literature explodes with suggestions for frameworks, scale metrics, and approaches, how you could systematically assess your model, but we're simply not able to do it. It is simply too technical. That's basically what it comes down to for most of us. So we basically have a systematic lack of funding to involve IT personnel to have these big beastly marine ecosystem models run across legacy hardware, because hardware is expensive, IT people are expensive, academic wages are often not sufficient. And even if you have the people, where do you get the cluster space? So it is a compound problem that is basically become institutionalized in the way we work. So we thought let's go back to the drawing board, and maybe we can come up with something simple that we can use existing IT structures to deploy our models countless times without relying on big funding or IT people. Could you do something with that? So we basically conceptualized it like that. That figure captures it quite well. And an assessment of an ecosystem model could be a simple scripted process where you run a bit of R, you run a model, you analyze. Everybody has their own favorite workflows, and some of them have been discussed here. How you could do an assessment. It would be ideal if you can automate that on a computer. It would even be better if you can automate it across multiple computers or even over fancy hardware. That's basically the idea of this slide. There's a few constraints here. Most, for instance, computing clusters don't allow models like we build to run because they're very badly programmed. They're wasteful. They don't optimize for hardware. That is also an artifact of the way these models are constructed. I mean, we've got cascading effects through food web ups and down. And as Tushit, who's in the audience here, said once, is like an ecosystem model is not a series of lambdas. You cannot cut it up in little pieces. It doesn't work. So you need to do something else. So you cannot optimize marine ecosystem models for hardware or for mathematical optimizations. You just have to use these beasts as they are. But you want like to, if you're a scientist and you have favorite statistical tools you want to use, you cannot recode this as well. All the tools have to be left intact. Instead, you optimize what you run and how and what you analyze. There you can make your gains. So, and you want, of course, simple to operate, open source, KISS, keep it simple, stupid. I mean, keep it as simple as possible. That was the aim. See if you can do something very simple to do the biggest challenge that we have been basically banging ahead against for 3 decades. So I won't go too much in detail. I hope this presentation will be made available to you afterwards and the paper's out. But the idea here of this figure is that it's a 4-layer system. The framework is the second layer, simple server client that you give a workload of what you want to do as a big text file.
that says, okay, I want you to, run your R script on these variables, put the output there. Now, next tool, pick it up, put it there. And then run your ecosystem model and your output goes there. It's all in text, similar to what Dave showed, actually. It's not unlike what Dave Jagari showed with his scripted work. And then the application framework on top is just totally disconnected from the framework. That's your statistical tools, that's your Ecopath model, Ecospace, and then you need some kind of structure to put the data back and forth. This is the heart of the framework in concept. And it, of course, has to be operating system agnostic, and it has to be secure and all these other tools. But okay, and this is in principle nothing new, but this is a simple version, a stripped down version of remote execution, commercial execution frameworks that cost you a ton, and this is free. So we decided to apply this thing under the Triatlas project, which has the aim to see if the uncertainty in Earth system models could, if you include that uncertainty, internal uncertainty in marine ecosystem model, Earth system models, in marine ecosystem models, would you gain better predictability? So this is interesting because when you run ecosystem models, when you have a very good calibrated situation, your initial values are good, but that only gives you so much a predictive window, because at some point a noise takes over the initial value problem. And if you have models that run the long run, climate scale, your model is more conditioned by the big assumptions regarding climate, and the internal variability doesn't matter anymore. But the intermediate bit is where the practical decisions take place, and there we're doing horribly. The Earth system model community has a strategy of dealing with it. It's like, okay, if we apply that to marine ecosystem modeling with this framework, does that make things somewhat better? So what the Earth system modeling world does is they call it the retrospective predictions. So basically every year, at a given point, they branch out. They have this baseline conditions, observed conditions, and under a set of agreed perturbation protocols, bring out feathers if you want, like for 10, 15 years, different versions of reality, check how well they behave. If the model does underperform, does the model need calibration adjusting? Well, what if you were to put those feathers through something big and nasty, an ecosystem model? What would you get? That was the whole aim. So what we did here, we used two marine ecosystem models, EC Earth and North CPM, under Triatlas. We used EcoOcean, the MAM that we're building with Willy and Marta and others, which is a global, speaking about picking the model for the right size, right? This is a global ecosystem model, 51 functional groups. But of course, because functional groups are very different in the Arctic than in the tropical area, we have all these systems in place. It's a heavily modified version of Ecospace where we bring in temperature adjusted metabolic rates. We take the behavior of groups into account based on the species composition that they have in the area you're looking at. So basically it comes down to having a different Ecopath model in every cell of an Ecospace scenario. That would be sort of what we're doing. And then what we did, we executed EcoOcean. It's calibrated to 1950. We ran it to 2015, but we only gathered output for the 35 years we had data for. 400 runs. So by all these feathers going individually for two ecosystem models for fish and non-fished oceans, just to gather data. We used a big hodgepodge of computers, 6 laptops and 2 desktops, and physically separated systems. And to show you how low tech this can be, we used Sync and Dropbox for the communication exchange between server and client. We wanted really not to have anything fancy here, because we want to show you don't need IT people to operate this. You have a text file, you got your tools, and bang, right? That's the idea. Simulations took a bit over 24 hours, but burned 1,600 CPU hours. That is way beyond what you can do in a single computer. But if you have a series of laptops lying around, it becomes feasible. So yeah, ton of data. Oh yeah, one interesting bit, the simulations produced about 5 terabytes of maps in 24 hours. That's a ton of data. But we condensed that into time series. We thought, okay, maybe we get some useful trends out of that. So this is the kind of stuff you're getting. Here you have EC Earth, there's North CPM. We have no fished ocean and the fished ocean, so the columns. And we only looked at the 3 Atlantic areas that Triatlas was interested in, area 2, 3, and 4, and the map there. And you see immediately quite stark differences. you see that here, these are the little feathers, right, that come through. You see that, yeah, easy earth, things are much more, the scales are different, but you see that fisheries has a profound impact, but there is a lot of difference. Well, it is very easy to analyze one model run, but 400, where you have conflicts about per system model, per area, which data are correct, right? So I just want to show with simple tools we can heavy lift, but what's next? And that's where this session has been mostly focusing on, thank God. So for now, I leave it just at the technical introduction that we've had. It worked. The use of Dropbox and Sync was absolutely painful, but it worked. I mean, that means you don't have to have your IT people. You can still do minimal means. Of course, the framework doesn't have, fail-safe structures that if Dropbox or Sync stop working, it was restarted. It can be made much more sexy, but the fact that you can do this with minimal means is a major step forward. So now we need to start worrying about, and that's what Sarah also showed, for instance, like, are ecosystem models producing correct results for the correct reasons? And Gideon was involved in a very nice paper, the HIPSI paper, which vouches for multi-level validation. So not only look at your output, but also check the internal state variables. Is this garbage? Is this plausible? And we can probably move much further on this. That was not my puzzle for this particular one. I just wanted to, take the argument we can do this out of the way, and now it's up to you guys. But yeah, it's a step forward. And I think, well, the utility, I hope, speaks for itself. So with that, thank you.
Thanks, Jeroen.
Nice.
Questions, very nice. And he's a student as well. Okay. Questions? So, Jeroen, how would you take this forward?
Well, there are several things you can do. I definitely I think this is a vehicle for scaling up what Dave's been working with, what we've been working with in these sessions to, can we get the stats better? Can we better explain why models behave the way they do? Because this can also be a step towards an automatic calibration routine. But what do you calibrate for what reasons? And yeah, as was already said at the beginning of this session, these models are complex, huge parameter space. Of course, you don't have to distrust all your parameters. You know what the sensitive ones are. You can do short breast perturbation experiments to identify the weak points and focus on those. You can do it systematically, but we need to work towards an automated routine or semi-automated to move forward. So, I mean, in that sense, the framework itself can be improved, but the stats, the things we throw on it, that's where the work lies. Yeah. Philly.
Jeroen, you said keep it simple. You also said it was very easy to set up, but you are a geek and you are a nerd. What about normal people who can actually do this? Anyone but you?
No, the whole idea is this is quite simple. The source code is available on GitHub. There is of course one aspect is of course how can you make your ecosystem model run in a structure like this? Stringing tools together in a text file is simple. We'll talk about in the scripting workshop on Thursday. We'll talk a bit more about what the implications are. Okay, how can you do what, for instance, Dave, what you did? You have an ecospace model and you have a command file. How do you make the two? How do you connect the two? That part is technical. That's unavoidable. Maybe in the next Ecopath version, Ecopath 7, we'll talk about it on Wednesday. We're considering ways to make Ecopath scriptable from the outside. We just build it smack into the tool itself, standardize the scripting capabilities. Once we have that, then this can be set up by anybody. Right now, there's a gap. Yeah, there's a hurdle. For the rest, it's easy.
Thanks, Jeroen.
Nice.
Okay, we'll move on to our last speaker of the session, last but not least. Yuriko is going to also take us into the future. Food web AI, creating, augmenting food webs with natural language models. Cool, thank you.
Right.
I'm loading the presentation.
You're confusing us by doing things that are not meant to be done.
Okay, sorry. Just a second. I'm just loading my slides. So, hi everyone. I'm Eurico. I'm a postdoc from Federal University of Rio Grande do Norte, Brazil. And today I'm going to talk about Food Web AI, which is an application that I have developed that uses artificial intelligence to build food webs. So, as probably you all know, creating a food web can be very complex to build the model because it is hard to get the data, to find the data, and to assemble all the right pieces and connections to build a food web. So it can be very challenging. So what we are proposing here is to use artificial intelligence with the new AI tools that are available, like from ChatGPT and others, to use these tools to get data from the web and put that together and build a food web with the knowledge from the web. So artificial intelligence is something that you are all probably listening a lot because it's a big hype out there in the media. And when we think about applying that to ecology, usually we think about things like computer vision or other methods. This computer vision, I also work with that methodology. It's a model that I have built for the Amazon. But for food webs, we're working with large language models like ChatGPT, with something it's already very mature, so it's gonna be like easier to use that to build a food web. So that's our goal, to build a user-friendly application that's able to build a food web. And if any of you have already used ChatGPT, you know how it works. It works with prompt engineering. You ask a question and it gives you the answer. So you're basically asking ChatGPT what are the trophic levels of the species, what are the trophic links, and then we put all of that together and build the food web. So let's take a look to the application. Okay, I'll just reload it. So here we go. It's the application. You can see there is a small introduction from what the application is. And clicking here in the food web part, we can choose, we can play a little bit with it. So there are 4 types of inputs that we can work with. So let's start with Ecopath, which is more familiar to everyone. So let's open the data. So this is from Ecopath. We can work with 2. We can export from the software 2 data that we have, like the basic estimates and in the consumption table. You can export that directly from the Ecopath. And then sorry, the internet's not. I'm gonna reload it because the internet failed a little bit. So here we go. Let's see if now it's gonna work. It's breaking, I'm sorry. So let me try another part of the software. Let me continue. So what it's gonna do is gonna build the food web from that data. So let me try another approach. I'll try Ecopath later. So let me show you the food web AI part. So from the food web, the idea is just giving the software a list of species and let it iterate over those species and build the food web from scratch. So let's see if the internet is gonna allow us to load this one smaller. So I hope it does. The software is not very heavy, so it should work fine. So we're putting the data, it's going to the server, and it is using the ChatGPT to ask many questions to the AI. So it then is going to assemble everything and creates the food web. So after doing that, you can see the entire food web was created using the AI. We can play a little bit, like changing the type of the chart that you want to work with. And we can also like choose the theme. So we can make like the chart a little bit prettier based on your own taste. And then we can you can edit the chart if you want to. So the table is right here. It's an editable table. So just change all the inputs and that's gonna update the chart as well. So as you might know, AI is still on its early stages, so it still hallucinates a lot. So it can provide a lot of false results, and it does. So we have tested the accuracy from the models. We use 3 cases, one from a database from the Arctic, other from Chesapeake Bay, and another from the Amazon. And we try to see how accurate these databases they were. But before getting that, let me just try to show you other functionalities for the software. We also have like these other types here, like this one's manual. It was built because sometimes, I don't know if we're teaching or for a lecture, maybe we don't have to build a very complex model. Sometimes we just want to build a food web just with some basic concepts. So you can do that manually here in the software. So you can add some rows and you can build the food web step by step, putting species names and things like that. So it will allow you to build some more conceptual model just to a presentation or something like that. Okay, so well, and the last one was Ecopath, but it is not working, unfortunately, because I don't know, it works. Let's try again. Okay, it should. I can show you later then. Yeah, over lunch I can show you. But it was gonna basically to open the same food web from Ecopath, and we could like play with it, build a more like beautiful food web, use different themes and so on, and use AI to provide you with like links and things like that. It's sad because it's not working, but let's move it on. So let me show just a little bit of the testing that we have made. The results. So these were the 3 food webs that we have tested. from the Arctic, Chesapeake Bay, and Amazon. And for the Arctic, I'm sorry. And for the Arctic, we have like the food web was able to guess with 100% of the time everything, all the trophic levels for all the species. So it was going to say, well, one species it's level 4 or the 3 or the 2, and we have compared this with the model from Ecopath. So it was able to guess the positions correctly. For Chesapeake Bay, it was able to guess 76% right. And for the Amazon, it's a experimental one. It's not published yet, but with our model that we have developed, it was able to guess 93%, so correctly. For the trophic links, that's a little bit more complicated because it's more data, and it is a little bit more difficult for the AI to guess who is gonna consume or be consumed by whom. So, well, even so, it was able to predict like 79% for the Arctic, 76 for the Chesapeake Bay, and 68 for the Amazon. For the Amazon, the data from the models are a little bit more or less unknown. So maybe that's why it struggled a little bit more. And we did a correlation with the Ecopath model. So we have for the Arctic, with the same trophic levels from the Ecopath. So we have for the Arctic 87%, Chesapeake 66, and the Amazon 85. And that is the last one is the proportion compared to the Ecopath model. So the proportion for the gases, it was like 55%, 29 and 21. So it was a little bit more difficult for the AI to guess the links compared to from an Ecopath model. So it struggled a little bit more. So basically, the app is going to be able to create these nice visualization, nice food webs. You can play with it. You can play with the themes, and you can use AI to try to enhance that. So unfortunately, I'm very sorry I wasn't able to show you everything that it does. It does a lot, but we still have a long way to go because AI is still in early stages, and what we're doing is still something very experimental. So it's something that we don't recommend to anyone to just put a list of species and try to publish that. But it's a good reference so to compare to your own models, and in the future we hope to also to make some improvements, like you put like the data, and it also provides the links, the papers that it is getting that information from. So maybe sometime it will like improve your workflow, make it better. So make it better to find information. So we hope that we have submitted the manuscript to Methods in Ecology Evolution. We'll hope that soon have that or that ready for you very soon. Okay. And the link is going to be available in a couple of weeks, like 15 days or so. So that's it. Thank you, everyone.
Interesting, really cool. Questions? Yes.
That was really cool. Thank you. I was going to ask actually about whether you pull any information about where the data comes from, but I guess you say that's coming next. I was just wondering, is there a risk of cannibalism here, where the tools pulling information from, if we've got an Ecopath VXC model that's been heavily published online, is it likely that it's going to go and find trophic levels from your model, bring it back as an AI, and then you're comparing apples and apples?
Yeah, well, the data that OpenAI uses, they don't really make that really clear to us where it's coming from. They say they are training from Wikipedia, some published papers, and so on. But we hope to improve that because we can use transfer learning to improve the predictions. So we hope to take like data from Ecobase or someplace to try to improve the predictions. This is one of the next steps that we have ahead.
Thanks.
Great presentation. I wanted to ask if you have already or are planning on testing it with any species for which intentionally misleading data might have ended up in the OpenAI training set. When I tried to use ChatGPT for some sort of socially controversial species, I got results that were very clearly influenced by Reddit posts and phishing forums online and things like that.
Yes, that's one of the problems that we are facing. It might get some wrong data from the web. It happens. It happens to us. Maybe for the Amazon data, we don't have much data published. So it happened a lot, like just something published in a place that we cannot trust.
Be really cool if you can figure out a way to filter that.
Thank you. I was wondering, adding like going with this technology advancement is good, and it was really interesting. But I think on the other hand, I see measurement has its own error, and process in the modeling, food web modeling has its own errors, and also OpenAI models has its own errors. I see this way like adding another level of uncertainty to the model. So how do you gonna address these uncertainties?
We cannot. At the moment, at least at the moment, we cannot. It's something, as I said, it's something very early stages, and it's still very experimental. But it is important to start from somewhere, and then we can work and improve.
If I'm allowed to reply to that, because I'm involved in the same work, I think this is now more a tool for information discovery rather than providing you with the truth. That they were far away from that. But it's interesting to see where this tool might pull the data from. It might lead you to interesting papers. There's nothing. It's a nice exploration tool.
Where it gets the data from.
It does.
Does it?
That's what we see.
So last question. Thank you. It applied a little bit to my questions. My question it was that with the development with AI in the future, we expect to have more data generated with AI in internet than data generated by us people. So this model or this framework in 5 years perhaps will use data generated by another AI, and it will be perhaps difficult for us to interpret the results. What do you think about it?
You mean like using data generated by?
Yeah, the risk of this kind of framework. If
well, it's something that it is possible to control, because we can take the model and we can like fine tune with what we want. So it is possible to work with transfer learning with this approach as well. So we can like, okay, let's establish some limits to the model, and let's make it just work with the data that we're giving it to. So we can refine that to get better results. So I understand it's something that we should concern, but it's also something that we can address. We have the tools for that. Thank you. Thanks. Thank you.
Thanks everybody. That's, I think, the end of this session. You're looking at me confused, but that is indeed the end of the session. So now we are going to do the photo first before we get lunch. So if you can all form a well-planned line out to just outside the front door, and we will do the photo there, please. And then we have lunch just in the coffee room where the booths are.